Welcome everyone to our solar photovoltaics course. Today we have 8th week and 4th module. So, in the last few lectures we have discussed about the vacuum technology. We have seen what is the need for a vacuum in a system and how we can create the vacuum, and also we have seen how to measure the vacuum, and if we have a leak in our system, how to detect that leak. Now, I have said in the last lecture that in addition to this vacuum technology, another important characterization tool which we will be using again and again as far as the solar cell is concerned is the advanced imaging technique. Now, whenever we talk about the imaging, we know about the optical microscopy based imaging things. So, that we have commonly used, everyone has used that. But optical microscope has some resolution issues. It has some issues in terms of the resolution which does not come from the instrument, but that comes from the fundamental diffraction limit of the optics. So, to circumvent that, people have been working for designing a new modalities of the imaging system which has led to the different varieties of the scanning probe microscopy system, where the electron beam instead of an optics beam or a photon beam is used as a probe beam to look at the sample. Now, out of the different scanning probe system, scanning electron microscope or SEM is commonly used for characterizing the morphology and the features of the materials. So, today we will discuss about some of the parts or some of the working principle of the SEM and how we can use the SEM to characterize a solar cell. Before we go for the SEM, so as I said that in an SEM we use an electron beam. So, we go back to our very early lectures where we have said that just like a photon can be represented by a wave, similarly an electron can also be represented by a particle. So, for example, we have seen that a photon beam which is a particle, right. So, that can be represented by a wave. So, or in other words, like electromagnetic wave, that can be represented by a particle. And similarly, an electron beam which is a particle, that can be represented by a wave which is the de Broglie wave or matter wave, and we have learned that this de Broglie wave lambda, that is equal to h by p, where h is the Planck's constant and p is the momentum of the particle. Now, this lambda can also be written as hc by E in the case of the massless photon, and lambda you can write it as h by 2 m, where m is the mass of the electron into q, the charge of the electron, times the V0, the applied potential difference, times whole half. This is for the non-relativistic case. For relativistic case, we have to do the relativistic correction. So, lambda is equal to h by 2 m electron q0 V0 plus q square V0 square by c square to the power whole half, that is for a relativistic case. Now, 10 kilovolt, that corresponds to 0.12 angstrom, and 100 kilovolt, that corresponds to 0.037 angstrom. So, depending upon whatever the resolution we are looking for, so we use that kind of excitation potential for the electron beam. Now, imaging needs contrast. So, if I have to have a very good image, we need a contrast, comes from any kind of interaction with electron beam. It can be topography, it can be composition, it can be elements, it can be phase, it can be grain or crystal orientation, or even charging, that affects the contrast. So, the topography of any image, so topography means the top features or the textures of the image, that also needs a good contrast. The composition, like let us say I have a perovskite material, a common organic inorganic perovskite CH3 NH3 lead iodide. So, the composition also affects the contrast. Elements, what kind of materials we are using, that also affects the contrast. Phase, so what is the phase of the system, that also affects the contrast. Grain orientation, whether the crystal grains are oriented parallelly or in a particular fashion or they are random fashion, so that also affects the contrast. And also the charging effect, if it is an organic material, then there is a possibility of charging, if it is an inorganic material, the charging possibility is less. So, those all things actually change the contrast. So, that means those all things can change the quality of the image. What are the advantage of the SEM over optical microscopy? Now, to begin with, so in the optical microscope we use a optical beam, and there the source of the light is photon beam. And what happens, like either if you use an upright microscope or an inverted microscope, so a light beam comes and they interact with the sample. Interaction means they transmit to the sample and we get a the inverted image of that object. Now, the magnification in an optical microscope, which is written here as OM, that is usually 4x to 1000x, although 1000x magnification in an optical microscope is very difficult and rare. Usually the normal inverted microscope, fluorescence microscope, we use it for 4 different light cubes and with that 4 different magnifications, 4 is 10x, 20x, 40x and 100x. In the case of 100x we also use the oil, but going to 1000x is sometimes very difficult, although it is possible. Whereas in a scanning electron microscope, which is an example of an electron microscope, the magnification is 10x to 3 lakhs x. So, you can go to really large magnification. The depth of the field here is 15 to 0.19 micrometer in the case of optical microscope, but in the case of the ACM it is 4 millimeter to 0.4 micron. So, the depth of the field is also very low. The resolution of an optical microscope is 0.2 micrometer, whereas the resolution of an ACM is only 1 to 10 nanometer. So, the resolution of any optical microscope, if I write it as resolution, that is lambda divided by 2 into numerical aperture, where lambda is the wavelength of incident light. Now, if I even use a very best quality film, the numerical aperture, let us say we get 1.5. So, that means the resolution R, that is lambda over 2 into 1.5, or R is equal to lambda by 3. So, what is resolution? Resolution is the capability to resolve the 2 points in an image. So, let us say I have an image like this. So, how good or how closely I can separate these 2 points, that gives the resolution of the system. Now, let us say I have a features in a scale of 100 nanometers. So, this distance between these 2 points is 100 nanometer, and I am looking at this system with a light of wavelength 600 nanometer. Now, according to this formula, using the light beam of 600 nanometer, the maximum separation between the 2 points which we can observe is 600 divided by 3, that is 200 nanometer. So, that means if I have to look at features in a scale of 100 nanometer, that I cannot use, that I cannot do it by using a 600 nanometer light, and look that it is not a problem of the light, or it is not a problem of the optical system, it is not a problem of the lens, or not how we have organized our optics. It is actually a limit, diffraction limit of the systems, beyond which it is not possible to resolve 2 components in an image. But if you use electron beam instead of a light beam as a source, then it is even possible to go to somewhat around a 10 nanometer scale. Now, this is only possible when you consider the electron not as a particle, but as a wave. Now, that was the triumph of the quantum theory. In quantum theory, in contrast to the classical theory, a particle like electron is considered as a wave, and we said that we represented the electron as a wave function, and we defined the probability. We said that the probability of the electron for in a particular space is more feasible or more realistic way to define its position, rather than telling that electron is at a particular position at a definite positions, right. So, when we consider the electron as a wave, then it was possible to use the electron beam as a source of the excitation beam, and in electron microscope this is exactly what it has been done. Here, instead of a light beam, we use the electron beam as a source of the excitation beam. Now, just like in an optical microscope, light beam comes and that interacts with the sample substrate, here also electron beams comes and interacts with the sample substrate. Now, the depth of the field comparison, if we do an optical image and an SEM image, let us look at these features. This is a image of a virus. If you look under the optical microscope, you can't resolve the each and every component here because of the diffraction limit, but if you look it under an electron microscope, you can see it each and every features. Now, let us say for a solar cell devices, energy materials, I made a perovskite thin films, and I need to see whether the grains are uniform, whether it is continuous and large. So, and the grain size we know it is, let us say 80 to 100 nanometer. So, obviously by using this optical microscope I will not be able to get a good image of this perovskite grains, but if we use a scanning electron microscope, then I can know what is my grain size, what is the composition in the grain. Even I can optimize, I can do the grain engineering, or I can do the morphology optimization to find out the proper morphology, so that the photophysics is also supported. So, that is the importance of the SEM in the solar photovoltaics. So, some of the main application of the ACM is the topography, the surface features of an object and its textures like hardness, reflectivity, etc. Morphology, the shape and size of the particles making up the object, strength, defects in IC and chips, etc. Composition, the elements and the compounds that the object is composed of and the relative amounts of them, melting point, reactivity, hardness, etc. Now, it is worthwhile to mention that in many times along with the ACM there is a one more module is attached, that is called EDAX, X-ray diffraction spectroscopy. So, basically this EDAX is used to do the elemental mapping. So, that can tell you what is the composition of the different elements inside the material. And then crystallographic information, how the grains are arranged in the object like conductivity, electrochemical properties, strength, etc. So, these all properties or all this information of the features or all this information can be obtained by using the ACM. Now, in an ACM setup, so then electron beam is allowed to interact with the sample specimen. Now, whenever the incident beam interacts with the sample, so many factors can happen, so many phenomena can happen. So, the ACM setup, an electron or specimen's interactions when happens, when the electron beam strikes the sample, both photons and electron signals are emitted. So, there is a lot of different possibilities is there. When the electron beam is hitting the sample substrate, that means the photon beam is here, instead of the photon we are using an electron beam. So, electron beam is interacting with the sample substrate. What is the sample substrate? A layer of the atoms. Now, what can happen? Firstly, it can happen the emission of the X-rays through the thickness composition informations. So, we know that X-ray can be continuous X-ray or characteristics X-ray. Continuous X-ray is the deceleration of the accelerated electrons, and then the characteristics X-ray where the electron is ejected from the inner orbits. So, both of this case we will get an information about the sample composition. Then there can be agar electrons, the surface sensitive compositional information can be obtained from there. There can be primary backscattered electron, which is the atomic number and topographical information. There can be cathode luminescence, which gives about the electrical information, and finally it can be secondary electrons also, which gives the topographical information. In ACM mainly we look for the secondary electron, which gives the topographical information. So, for example, if you look at this electron orbit, this is the nucleus and the electron is rotating around k, l and m orbits. Here we are just showing k, L1 and L23 orbit. Now, whenever the electron ejected from there, so then electron jumps from the inner orbit to the outer orbit, and if that electron ejected, then you get a secondary electrons. So, the real schematic diagram of a scanning electron microscope is very complex. As you can see from this figure, we have an electron gun here. So, this is the electron gun which emits the electron beam, this one. Now, in an optical microscope we use a lens to collimate the beam. Now, in an electron microscope we cannot use the lens to collimate the beam. Here we use electromagnetic coil, and this electromagnetic coil serves as a lens and they actually collimate the beam. So, the first condenser lens C1, so that helps to collimate the beam, and the second condenser lens C2 that further helps to collimate the beam, and finally the collimated beam falls on an objective lens O, which is situated here and which is also connected to a scanning coil, okay. And the scanning coil is connected to a magnification control unit, and the magnification control unit is connected to a scan generator. So, basically the scan generator do the scanning, and a beam banking coils is attached to the scan generators. In the electron gun we apply a high voltage like 20 kilovolt. Below the objective lens there are X-ray detectors in the case of EDAS, and then there are different detector there, but first there are the specimen, the sample substrate, and this is the specimen chamber which is stayed in a very ultra high vacuum, and these are the pumping system, vacuum pumping system, diffusion of the turbomolecular pumps. We said that when we do the ACM we usually maintain a very high vacuum, right, because the electron is allowing the interaction or the scattering with the another atomic layers. So, basically we have to make sure there is nothing else inside the chamber. Now, the detector, they can be different things. Now, basically we are looking for the secondary electron. So, that is why you have a secondary preamplifier, and then we have the backscattered preamplifier, and we have a specimen current preamplifier. Now, these are all connected to a selection switches which is connected to a video amplifier, and finally it goes to the display CRT and the record CRT which is displayed in the camera. So, if we look the whole picture, so basically there are 3 to 4 main components is there. One is the electron gun which emits the electron at high voltage at 20 kilovolt. Then there are condenser lens and objectives, these are the optical components which helps to collimate the beam. Collimated beam falls on the specimen substrate, and whatever the electron is ejected, that is detected by the detector. It can be an X-ray detector or it can be a secondary electron detector, and by doing some magnification we collect the image by an image acquisition system. It is shown in the camera. So, there are 4 parts in there. One is the electron gun, another is the optics, another is the specimen sample chamber where you keep the specimen under the vacuum, and then there are some detectors is there, and all the system is kept in a high vacuum 10 to the power minus 4 torr to 10 to the power minus 6 torr. So, that was the circuit diagram of an ACM, and in terms of the magnification we also gain a lot. For example, like let us say IS is the beam which is falling on the specimen, IS is the electron beams and it is the scan distance on the specimen, and LD is the sweep distance on the monitor. You are using a CRT. So, LD is the shear distance and IS is the electron beam scan distance from the objective to the sample specimen substrate. Most of the cases it is kept at 8 millimeter. Now, the magnification is defined as LD by IS. So, the sweep distance divided by E beam scan distance. What about detectors and brightness? So, there are a lot of detectors are there, but mainly we are talking about the secondary electron detector. So, you look at this figure, like this is the specimen sample substrate on which the beam is falling. Now, the secondary electron is ejected there. Now, we put a scintillator. The scintillator collects the secondary electrons and there has been kept in a Faraday cup, and there are light pipe which is connected to a PMT or photomultiplier tube, and this PMT tube is biased by a PMT voltage supply, and there is a scintillator voltage supply, there is a scintillator voltage supply which bias the scintillator, and whatever the light comes from the scintillator that goes to this PMT, and the PMT is connected finally to the image acquisition systems. So, basically the beams falls on the sample specimen, it ejects the electron is collected by the scintillator and then it enters to the light pipe, finally it goes to the PMT and the PMT is connected to the image acquisition systems. Now, in this figure we are showing it here what will happen if we put a primary beam and detectable emission zone for secondary electrons. So, for an average signal, so this is the distance the beam can penetrate. If I have a very strong signal, then the distance will become more and more. If it is a strong signal, it can goes until this point. If it is a weak signal, because of the hole, it can only penetrate a small distance. Now, what can be the source of electrons? The source of the electrons are called thermoionic guns, because they emit the electron by heating the coils, by heating the filament. So, that is why they are called thermoionic gun. Okay, they are electron gun. So, they have been placed in a cylinder called Owen held cylinder or grid, and there are the anodes, filaments is there, and some of the parameters for the source and brightness. For example, if you use tungsten, the brightness is 3 × 10 to the power 5. If you use lanthanum boride or lanthanum B6, this is 3 × 10 to the power 6. Similarly, for CFEG and tungsten FEG, it is 10 to the power 9. Okay. So, electron gun properties, it is usually represented in terms of the stability and also in terms of the size energy spread vacuum, which is tabulated in this table. Now, in most of the cases, the field emission gun that has an energy more than 10 millivolt per centimeter, and if we use an organic sample, we have to tune the voltage of the electron gun. So, here we are showing the thermoionic emission gun. As you can see, this is a filament and this is a filament heating supply, and the whole filament is put in a grid cap cylinder, and there is a biasing is happening to the filament supply. Now, the electron is ejected and it goes to the electrode plate. This is the 2 electrode plate, and which is kept under the a voltage difference with respect to the cathode, and whatever the electron that comes, they goes in this solid angle. So, a tungsten filament heated by DC to approximately 2700 Kelvin or LaB6 rod heated to around 2000 Kelvin. A vacuum of 10 to the power minus 3 Pascal, 10 to the power minus 4 Pascal for LaB6 is needed to prevent oxidation of the filament. Electrons boils up from the tip of the filament. Electrons are accelerated by an acceleration voltage of 1 to 50 kilovolt. So, basically we use a tungsten filament or LaP6 filament. Both the tungsten and LaB6 filament needs a high vacuum. Now, if we heat the filament, electrons are ejected, then there is a potential difference between the anode and the filament which collects the electron, and electrons start ejecting in a solid angle. and the electron comes to the condenser lens, and the condenser lens will collimate the electron beam. In a field emission gun, the tip of a tungsten needle is made very sharp, radius of less than 0.1 micrometer. The electric field at the tip is very strong. So, if you make this kind of tip, the electric field at this tip will be very sharp. It is about more than 10 to the power 7 volt per centimeter due to the sharp point effect. Electrons are pulled out from the tip by a strong electric field, and ultra high vacuum better than 10 to the power minus 6 Pascal is needed to avoid ion bombardment to the tip from the residual gas. Now, there can be gas inside this chamber, since there is a very strong electric field at the top of this tip. So, there is a possibility of the bombardment of the gas with the tip. So, to avoid that, we use a ultra high vacuum in a field emission gun. So, field emission gun is more sophisticated than a normal emission gun or a normal thermo emission gun. So, today we have discussed with you about this the working principle of a scanning electron microscope and the different components of a scanning electron microscope, and as I have said that SEM or scanning electron microscope is commonly used to know the morphology of the systems. Now, since we have learned that morphology of any kind of solar cell is very important to optimize the efficiency, as the morphology is directly related to the photophysics of the system, that is why whenever we make any thin film, before making we device, first we look it under the SEM to look its morphology. So, in today's lecture we have discussed about what is the need for the SEM in a solar cell device and what are the different components of the SEM system or the scanning electron microscope. In the next lecture, we will discuss about one important techniques of the solar cell characterization, that is impedance spectroscopy based characterizations, and we will see that in apart from some standard characterization, this impedance spectroscopy techniques has emerged as a very new technique for the characterization of the electrical parameters of the solar cell. Thank you so much.